Good evening, everybody. Let's get started. Just to note, let me start recording. And also, this is being online streaming to the YouTube for a couple of students. They haven't got Canvas access yet. So for them, I need to stream it into the YouTube just for your note. Then let's see. We have our very first topics tonight, which talks about computer system and organizations. So can you guys hear me okay?
Yeah, we can hear you.
Okay, excellent. All right. And also, like, our focus mode is on. That means only me can review your videos. No other student can view your video. So it is just between you and me. So thank you for turning on your cameras. I can see faces. That's good to see all the faces there. Thank you. Okay. We have quite a lot participate here. Let's start with a quick poll for a minute. Let's see how we are doing on our study. Okay, what is this one? Okay, all right. Very simple. 2 questions. You can answer it anonymously if you want. Let's take a minute to answer these questions, and I'll share the result. I see 84 of 97 have participated in that poll. It has 2 questions. Number 1, have you watched lecture videos, read lecture notes? And for the today's topic, and another question was, have you noted down your query into the corresponding discussion page? I think you are almost done. Let's end the poll here and let me share the result with you guys. So 51%, half of the class said, yes, you have reviewed the lecture videos and notes, all of them. 42% you said some of them, and 7% says none of them. So for none of them, please make sure you review the lecture notes or videos before coming to the class. Otherwise, discussion may become really cryptic for you guys. Whoever has done partial review, thank you. Please try to do full review before coming to the class. And thanks for all those who have actually done it, the pre-work, before coming to today's class. Okay. So let's see. If I ask a question like, what is a computer? Can someone volunteer to answer that? Anyone? Yes. On.
It is something that computes.
Okay. That's a good definition. Something which computes. It necessarily may not be an electronic device. It can be anything compute, anything who can compute, including ourselves as a human. Okay. Can someone volunteer to tell me, what are the major components of the computing system?
The major components are the central processing unit, or the CPU. There are also input devices and output devices, and also memory devices.
Okay, excellent. Thank you very much, Alex. That's good. Okay, so basically, let's do one thing before we quickly review the lecture slides today. Let me show you how a simple program works in a computer. Does anyone know like how a simple program works inside a computer? Wants to briefly tell us if you know? Or what's your idea how computer works?
So, can you guys hear me all right?
Yes, we can hear you.
All right. So, from my memory, it's that there are memory addresses, and then basically a computer can modify the values of one memory address, read and compare the values of a memory address, and then and jump from different memory addresses. And using that in conjunction, like with each other, you can do all sorts of computations.
Okay, fair enough. Okay, anyone else? Any other viewpoint than him? Austin, right? Austin Chen? Is that your name?
Yes, that was me.
Any other viewpoint than Austin? Yeah, I don't expect you guys to like know that. Like you are here to know that exactly, learn about that, right? I just wonder if you have any pre-ideas about that thing. Okay, so let's take a quick look and try to understand what really goes inside a computing system. And through that example, maybe we would be able to understand what are the different components, major components of a computing system, and what is their role, exact role in the computing process. Okay, so let me share my screen. Okay. And okay. Oops, not this one. No, this one. Okay, whoever is turned on the caption, thank you very much. I forgot to do that. I thought it is auto-enabled, the caption. Seems like not. You guys now can see the auto caption, right? Yes, no, maybe?
Yes, yes.
Okay, thank you for confirming. Okay. All right, here is it. So a memory, let's take a quick look what a memory is. A memory is, you can think of as an index storage, just like array, like an integer of array. If you think, like, I believe all of you have used that data structure, array, integer array, at some point of time in your programming life. You can think of a memory as an index storage, just like array. Okay, and it has another component, let's call it MMU, or memory management unit. So this guy together, this storage, physical storage, and this memory management unit, together it is a memory as a device, like conceptual part. So what we can do with the memory, we can ask memory to write or store something inside it, right? So we can tell that, hey, write number 5 at index 3. Okay, so what it will do, it will go and write the value 5 in index 3. Similarly, we can ask it, hey, write 13 at address 1, and it will do that. It will write that value 13 in index 1. Of course, like we say, we are telling MMU, means we are not really speaking up and like through verbally we are telling it. We are electronically telling memory management unit to do that action. So that's what it means. And the index the carry index, what we know all about till our software programming, we call in the hardware world, we call it an address. So when we call a memory index or memory address, they are basically the same thing. This is the index of that index storage that we're talking about. Okay, so this index or address. So here address is 1, here address is 3, and so on and so forth. Now, what else we can do with the memory? We can ask it, hey, read from address 1. So what it will do, it will, this guy will read from this address, value 13, and return it back to us. Of course, electronically, and not really verbally or written or anything like that. Electronically, it will transfer that value to us. Now, so this is all about memory basic function. Okay, very simple thing. Now let's talk about another component called ALU, or arithmetic logic unit. What this guy does, this is an electronic component again, and what it does, very simple operation we can ask it to perform, like what is 3 plus 5? Okay, and it returns 8 as an answer. And literally it is very simple, like it only can perform handful of mathematical function like addition, subtraction, multiplication, division, and handful of logic operations. If you recall your math 42, we have different logic operation like AND, OR, XOR, NOR, etc., or NOT. Those operations it can perform. It doesn't perform any other complex mathematics operation or logical operation. Very simple. Only 4 categories of mathematics: integer mathematics like addition, subtraction, multiplication, division, and very basic logic operation like XOR, NOT, AND, OR, etc. Nothing else. Then let me introduce another part which is very similar to the memory, okay, but very small in number. Okay, memory can be really big. This index storage can be really big. Like nowadays, your laptop has what, like maybe half a terabyte memory is, or maybe 500 megabyte. I don't know, like 1 gig memory, something like that, which is a huge storage. Whereas this piece of memory, we call it a register file, and available only handful, like 32. Maybe 64, in some system it has 128. They are very fast memory, okay? And it resides inside the processor. Like when we talk about Pentium processor or ARM processor or Snapdragon from the Qualcomm processor, this register file resides inside. It's a part of the processor. It's just a memory, but of very fast memory. So this guy is kind of a snail compared to this guy. Okay, this is really fast piece of memory, resides inside a processor. We call it a register file. But operation-wise, it is very much similar to the memory. We can ask it to write something, store something inside the register memories, and retrieve them back. Okay, so that's another part. Now, another component, which is possibly the most important component, is a controller. Okay, we'll see how the controller works for you to execute your piece of code. Together, controller, register files, register file unit, and ALU, we call it a processor. Okay, and they are usually enclosed in one physical integrated chip. Okay, like a Pentium, like ARM, like Snapdragon, and other like A2 from the Apple, and so on and so forth. Like a different company produce different processor chip. So in very much concept, a processor basically has 3 big components in it, and they have their specific purpose to execute your program. and the other component is a memory. Okay, so that's another piece of hardware which practically give you big enough storage to perform your computing task. Now, let's look at a piece of software. Okay? Language doesn't matter, but here the concept matter is like we are writing some variable, integer A, initializing it to 10, integer B, initializing it to 20, and integer C equal to A plus B. Okay. So we all know like what it will do. It will, at the end of the day, it will add these value 20 and 10 and store it in variable C. Okay. So now at this point, can someone tell me what is a variable? Like when you write a variable, what it is in terms of computer system? What is a variable?
Oh, sorry.
Anyone?
I guess like for a variable, it could be thought of as like a container to store information.
Okay. Right. So can you relate that to the hardware? Piece of hardware or your system? Conceptually?
Was your question, was it, what's a variable?
Yeah.
Okay, so I think I remember this. I was studying another language, and I remember that a variable in most languages has 4 values. It has a location in memory, like an address, a value, a type, and then a name. So it's basically just when a program says, okay, just keep this, like something, put something in this electrical location, right? And then it just stays there. And it can like destroy or do whatever it wants to it, right?
Okay. Okay, that's good. Hey, what's your name? I didn't catch your name from the canvas, from the Zoom.
Oh, it's Alex.
Alex. Alex, last name?
BUI.
Oh, BUI. Okay. Thank you, Alex. So I have a couple of Alex in the class as well. Okay. All right. Yeah, you're right in your concept. So let me explain it. So when we actually write something, declare a variable in a program, software program, what we are requesting the computing system to assign some piece of memory, okay, to me, and I will call it A, like aliasing a piece of memory. I call it a referencing as an A, okay? When I call something, write something like integer B, I'm actually asking the computer system to assign some piece of memory, which I will refer as B, and so on and so forth. Integer C means like, okay, assign me a piece of memory, which I call it C in my program, okay? So that's always the variable. So if something like this happens, like A, let's say, is assigned by the system an address 0, means this memory address 0, I'll call it A, and I will use refer A. Whenever I'm referring A in my program, actually I'm referring to this memory location. Okay, whenever I refer B in my program, I'm actually referring this index 1, this piece of memory in my program. And similarly, C, whenever I refer C in my program, I actually looking at a memory space, this, whatever this value contains, I operate on that. So that's the physical meaning of declaring a variable in a software program corresponding to the computing hardware system. Okay, it's kind of establishing that piece of memory and what I call it, refer it in my program. Okay, so here, now what will happen is a tool, intermediate tool called compiler, will act upon this program and dump some simplified step for us. Okay, and this is the assembly level programming. You guys are more familiar with the Java programming, and Java programming has compiler, but it works in a little bit different way. It generates something called a bytecode, which is more similar to what I'm talking about, these stepwise simple steps. Okay, bytecode. In Java world, it is called a bytecode. In like most of the other compiled programming language, example C, C++, that kind of languages, that tool is compiler. Okay, a compiler take a piece of high-level program like this and convert into more basic level program or instruction like that. This is not exactly the assembly syntax, but I'm just discussing that functionality of the compiler here, which basically breaks it down into smaller piece of code. Okay. Now, from here, another piece of tool comes in. Once these steps are jotted down by compiler, another piece of tool called assembler comes in, and which converts this instruction into some numbers, into some code. This is the machine code. Okay, so each of these steps or instruction are converted into some numeric number, which is called a machine code. And this is nothing but that your binary executable. Like, remember, you download some apps, download some program from internet onto a laptop, some exe program gets generated. Exe is nothing but glorified list of instruction like this. Okay, a series of numbers practically, which is understood only by controller. All right, so this is your executable. Now, when you start this piece of code, what happens? This machine code get copied into part of the memory. Okay, let's assume this piece of code is copied from memory address 3. Same piece of code, these instructions. All right. So far, so good. Any question? So we loaded the program into the memory. And now,
Professor, there's a question in the chat. They're asking why it's not in the binary.
why not in the binary? Means what?
The assembler output, right? It is, you, at least for this example, you didn't write it in, like, ones and zeros. I think that's what they're asking.
Yeah, this is for human readability. This is all binary. These are machine codes. Machine codes are all in binaries. That's a good question. I just wrote it down in a text form of it so that we kind of are not intimidated by the binary itself. Okay, it will be binary, a long sequence of 1 zeros, etc. Does that answer the question?
Yeah, it does. Thanks.
Okay, all right. So, okay. Now, another piece of component inside the processor, we call it a program counter or PC. Okay. What it contains, when you power up a computing system, it first contains a memory address from where the program start execution. Okay. So in this case, let's say it powered up at 3 because this is the start of the program. In your boot up sequence on your laptop, it has a predefined power up address, like Pentium processor has one, ARM has another, and Qualcomm Snapdragon has another. So each processor defines a power up address. And when you start your laptops or start your computing system, when it powers up with a predefined address, and your boot program actually get fetched from that address. Fixed address always. Okay, let's not get into that complexity right now. Let's just assume that this piece of machine code gets populated into the memory and this program starts. Okay, your program counter is set to 3, start of that program. Now let's look at the steps. So first thing this controller does, pick up this address value from the program counter and ask memory that, hey, read from 3. So memory returns that piece of machine code. Okay, the first machine code stored here. Then this controller kind of parse that and break it down into several pieces and infer that, okay, programmer wants it to write value 10 at address 0. Okay, so it does that inference and sent that instruction to the memory. Hey, write 10 at 0. Memory simply obey that command and write 10 into 0. So at this point, you exactly executed this high-level instruction, integer A. You have a variable initialized with value 0. Here is the initialization. And in the meantime, another thing happened, your program counter gets updated to the next instruction, to the next address, next instruction address, not in next instruction address, which is 4, right? So now controller give another read instruction to the memory, read from 4. Memory returns that machine code. Controller dissect that machine code and understand that, hey, programmer wants it to write 20 at address 1. Simply issues that instruction to the memory and tell memory, hey, write 20 into 1. So 20 is written in the memory 1. And at this point, we exactly executed this high-level instruction. We have a variable B initialized at value 20 here. And your program counter in the meantime updated to the address of the next instruction. The controller sent that address to read that instruction. This phase is called instruction fetch. It's fetching the next instruction to it. Memory returns it. Then it again like parse, break it down, this piece of value into several parts to understand what the instruction is, and this is called instruction decoding step. So instruction fetch, now it is doing instruction decoding. Instruction decoding, by decoding at this point, it understands what program wants to do is read from address 0 and store it into the register file 0. Okay, so how it does it? It goes and sent the read instruction to the memory. So this is a memory access step, okay, data part. It is accessing the data, not accessing the instruction, but it is accessing the data. The read from 0, memory sends that value 10 from reading from address 0. Now it will send, store or write instruction to the register file telling that, hey, write a value 10 at 0 for you. So register file 0 stores the value 10. Okay. PC gets updated to the next instruction. So it does instruction fetch again, get the instruction from the memory, do the instruction decode. So these instructions say that, hey, read from memory 1 and store it in register file 1. So it will send that instruction to the memory, read from 1. Memory returns 20. It will ask register file to write 20, that value 20 into register 1. So register file gets updated to value 20. PC gets updated to next instruction address 7. So instruction fetch, memory returns that instruction, controller decodes it, instruction decode, and now it is understanding that what program wants to do, fetch the value from register 0, fetch the value from register 1, add them up and store the additional value to register file 2, that at this point, at this area, storage. So what it will do, it will ask register file that, hey, give me the value stored at 0 and 1. Okay. So it's that is one thing. Just note the difference between a register file and memory in a register file, we can simultaneously read two locations. We can ask it to read from two locations simultaneously, and register file will return those two locations simultaneously. There's those two values stored in those two locations together. Memory cannot do that. Memory is always one by one. You ask for one address, it will give back value stored in that one address. Okay. Register file has a special device which can actually concurrently access two storage together and send it back to controller. That is one difference. Okay, so register file sends back. Controller then asks ALU, hey, what is addition result of 10 plus 20? Okay. ALU returns the result 30. It asks register file to write 30 at address 2. Register file 2. 30 get added here. Of course, PC get updated to the next instruction address. So it's do the instruction fetch. It asks the memory, read from the memory address 8. Memory returns the machine code. We do the instruction decode. And what it does, it now sees that the program wants to do read from register file 2 and store it at address 2. So it asks register file unit to, hey, read from your address 2. So 2 stores 30, it returns 30 to the controller. Then controller asks memory, write 30 to the address 2. So memory add that or stored that value to the 2, which effectively does this, right? Take the value of A and B, add them up, and store the result in variable C, right? So we had just done writing this, like executing your simple 3-line program. We spent half an hour to see what exactly does, what steps. And that many steps does, actually. You know, like to execute this simple step, a processor like MIPS, which we'll study in this class, will actually take, I'll say, these are the exact assembly program. Don't worry if you don't understand it, we'll learn how to write assembly program. But this piece of code will probably be translated at assembly level like this. So we have 1, 2, 3, 4, 5, 6, 7, 8. 8 low-level instruction, assembly level instruction, which will be translated into 8 machine-level code. And each machine code need 5 steps to complete. Instruction fetch, instruction decode, execute, memory access, and write back. Okay, these 5 things happens to execute one instruction. So that means we are looking for like 1, 2, 3, 4, 5, 6, 7, 8. 8 instruction into 5, 40 cycle, 40 steps happens to do this simple arithmetic of A plus B. 40 steps happens, all right? So that's how it works. Question? No question? Okay, let's take, yeah, someone?
People in the chat are asking if the register file is limited to accessing only 2 elements at a time, or if it can access more.
No, it is 2 elements at a time.
Is that ISA dependent?
What's that? Sorry.
The instruction set dependent?
Instruction set dependent means, what do you mean?
Like, you know, MIPS versus x86, for example.
It depends, but I don't see necessity of returning more than 2 in a piece of hardware. Like, you know, like if we add more and more return, like allow like 4 returns or 5 returns at a time, it will increase complexity in the underlying hardware. So 2 is sufficient for most of the processor. I'm not saying there won't be any exception to it, but most of the time it is 2 is sufficient.
Professor, where
Yes.
does the PC, what's the next address the PC does after it's done with all the instructions? Where does it go?
Sorry, come again?
What is the next memory address the PC goes to when it's done with all the instructions?
Oh, so it's basically that's an interesting question. How do I want to do that? Okay. See, when you boot up your process, your system, right? Okay, let me first answer your question. It does go to the next program address, like where it ended. It ended like address 8, right? So program counter will be updated to 9, and whatever instruction, if there is any instruction stored in that area, it will return it. It will keep on returning something garbage as well, okay, as a hardware, piece of hardware. Now, does your system works like that? No. What happens in your system, like when you boot up your operating system, right? And your operating system itself is a software program, okay? And what happens that when you start an user program, like an executable from your Windows operating system or Linux operating system, your program counter control temporarily transferred into the part of your that executable program code, and it just execute one by one, whatever it does. At the end of the execution, it controls return back to the operating system program code. And that program inherently has a loop inside it, okay? So it waits for the next action, next action, next action. So it does not fall back into a area where there is a garbage code or no op or something like that. So operating system is a software program which practically waits on your next steps to next instruction to follow. Does that answer your question?
Yes, Professor, thank you.
Professor,
Yes.
can I say it's like the Java program what we code after it got into the system is like can kind of be transferred to another language, and that kind of language which is like applied by the system like had its own operating way to like execute it. Maybe there's only one line of the code in the Java, but you probably will have like 3 or 4 more codes in the system compiler.
Yes. So basically, let's say, for example, right, in your Java, when you are writing a Java program, like simple println hello world, right? Let's just one line code. So that println that code that creates a Java bytecode, right? Which interact with the operating system device driver library to print that character onto the screen, right? So at that point, it goes out of your Java virtual machine and actually goes to the operating system part of the operating system library, which basically prints that code onto the screen.
Okay, thank you, Professor.
Does that answer your question?
Yeah, kind of.
Okay, all right. Those are good questions. Keep it coming. Okay, keep thinking on your question while we take a 5-minute break, and we will get back with the slide reviews. And I think I have one question. I saw one question on the discussion. I've answered that question already, but yeah, I will re-explain that. Oh, okay, let's get started. Maybe we can look at the lecture one, quickly go through it first, and let me know verbally, of course, if you have question, because I don't pay attention much to the chat. Okay, so what did we learn? Did I already sharing, right? Yeah. Okay. So we talked about different avatars of computer, like it's nowadays everywhere, right? We all agree to that. But all of them has this very simplistic view, right? It has a central processing unit, we call it CPU. It has some means to input information to it, and it has some means to output the result, like in the printer or on the screen or other means. And it accompanied with some memory devices and storages as well, I should say. Not only the main memory, but storage and disk, all these things are part of it. It's a real storage of this part, right? And if we look a little bit in a more detailed sense, like we can say that, hey, my central processing unit has many different components, at least the modern computing has. Like it has like a processor, it has a graphics processing unit, it has a network interface card or NIC, it has some IO card to connect to the input-output devices and some onboard memories, memory interface controller, etc. Like this is not limited to these components. There can be more or less depending on what computer we're talking about. And many of them has external connection to the devices through like USB ports is nowadays kind of ubiquitous. It's every system has USB 2, USB 3, and whatever, like USB-C, etc., etc. So we can connect all devices that support the USB port. We can connect and extend our peripheral devices around the computing system. And also it has this memory interface and external memory devices, like we can, apart from onboard memory, we can use all these solid state memory, the memory card, USB memory, etc., onto the system as well to extend the memories and storages. It has some sort of input device. Mostly, I would assume your laptop would have at least a keyboard, mouse pad or trackpad, something like that nature. And it has a screen which can be output and input device too. Like if you have a touch screen, that touch screen serves both as your input device and output device as well. And it has some external memories like disk drive and so on and so forth. So these are the detailed hardware view, but very nicely drawn and kind of very clean-cut view of that. But if we open the real-world circuit, it just looks like nothing like what we have drawn in the previous slide. It's basically very complex things, right? And someone can get lost into the whole system. Our target is not study these systems, this system as a physical as it appears. These are more like a computer engineering realm to, like really deal with the board and PCBs and real hardware connection. Our target is to more like understand the system from concept point of view so that we can tune up our software program for better performance in terms of runtime and in terms of memory consumption. Okay, so once you step into like real world industry and as you go up in your engineering career ladder, you will eventually end up in a position where your target is going to be like, okay, optimize your application to take less amount of memory, but it will run faster, right? That's how you'll have your competitive edge in the market. Okay, so that's why it is very important to understand the underlying hardware concept and how your software program works to better optimize your software programs in terms of memory consumption and in terms of faster runtime. Okay. Now let's look at our concept. Okay. So as we started, we had these different components and we are kind of modeling them through a schematic diagram like storage, memory, processors, input, output devices, and which has like input devices can be mouse, keyboard, display, output device can be display, printer, just example, not limited to only these things. It can be many things. And storage as a ROM and RAM, read-only memory, random access memory, different types of solid-state memories are there, and also disk drive, solid-state disk drive, for example. And these arrows actually shows the flow of information for the system. Your computing system is nothing but an information crunching, information processing system, right? So your information flows from input device to the inside into the processor, and processor sends back some information back to the output devices. And processor sends information to be stored in the storage and the memory and can fetch it back, as we just shown in the previous section, that how a simple program works. It continuously get in touch with the memory, swapping some information around or turning some information around, store it, fetch it back, restore it, fetch it back, and so on and so forth. So this is the whole thing. Now, oops, the next slide, what the next slide talks about, we are kind of merge these two into tell them, okay, we are modeling, instead of modeling input and output device separately, let's model it together. Let's call it input output device, IO device. Okay. And other part is storage and memory, that is the same thing. Now here, what we are dealing with, that these are all electronic devices like keyboard, mouse, display, printer, ROM, RAM, disk drive. Question is how a processor going to communicate this information to them or fetch an information from an IO device or push an information to an IO device. Okay, a processor needs to tell to some system that, hey, this information is for the display, not for the printer. Or this info, I want to fetch an information from mouse, not from the keyboard. It need to be able to do that. It need to be able to ask specifically a device, okay, give me input, mouse, give me your input, or keyboard, give me your input, right? And also it needs to specifically tell the memory system where to store your information or where from your information to be fetched in. As we have seen in the previous section, that sample small program, your controller as a whole, the processor inside the controller, it needs to tell memory exactly where to store things, exactly where from to fetch your next instruction, right? So it has to tell them. So mechanism is to produce an address, an unique value, which distinctly say that this address is for the display. This address value is for the printer. This address value is for the keyboard. This address value is for the mouse. This address value is for that index storage in the memory. Or this address value is for that specific disk, that specific track inside the disk, and so on and so forth. So addressing is a mechanism which used by the processor to distinctly send information exchange target in the system. Like whether I'm targeting keyboard, whether I'm targeting mouse or display or printer or specific area in the memory or specific area in the disk drive, it is all conveyed through this addressing mechanism. An address is a value. Okay, it's a 32-bit binary sequence or 64-bit binary sequence, depending on what system you have, 64-bit or 32-bit. But this is just a value, unique value assigned for unique devices or part of the memory. So now, in older days, okay, the mechanism also involved another special signal, which let's call it IONM. This is not a standard name, I just gave it. As a hardware designer, we have absolute freedom to define whatever we want to do. Okay, there is no written convention what signal has to name what. Okay, so the purpose of this specific signal is this, that if this value is 1, then the address I produce would be targeted for our input device, output device. And if the address IONM is 1, then it will be targeted for a memory. So that means essentially, let me just take a note. Let's say my address, it produced 10. Okay. And IONM, that signal value is 1. So that means that send, or in general, exchange the information with IO device indexed with 10. Okay, that's the meaning of it. So what is that indexed with? What is that device? Who knows? Maybe in that system we define number 10 as my display. Maybe, who knows? Just I'm giving an example. Okay, so that means whatever information the processor is sending out into the system, it's basically targeted for that IO device with indexed with a 10, if this is 1. Now, if it is 0, the same address value 0, what means, okay, exchange of information with memory device indexed with 10. Maybe that's storage 10, right? We just saw in the previous section, the memory is index storage. It is indexing from 0, 1, 2, 3, 4. So we are actually looking at that storage index 10 in the memory. So same address can be reused for a memory information exchange or information exchange with the IO device. They are a special signal, but it was used in the older system. Okay, in the newer system, that signal is no longer there. That signal is basically become a part of the address itself. Why? Older system used to be a very small system, like an 8-bit system or 16-bit system, right? So even with a 16-bit system, let's say this is a 16-bit system, our address space is 2 to the power 16, which is like, we'll learn about this computation and calculation, but I'm saying this is more about 10, 32, 64K kilobyte system. We can address only 64 kilobyte with this, right? So having one more signal like IONM actually give us edge of that I can use with IONM, using IONM, entire 64 KB can be used, right? On the memory space. On the other side, IO side, right? You don't have 64K devices. You cannot, like how many devices you can attach to a computing system? 10, maybe? 10 is too much, right? You have display, you have mouse, you have keyboard, maybe game playing joystick, maybe your race driving car steering wheel. I cannot think of any. Okay, camera. Let's come around camera, microphone. Keep on adding. Like you cannot go beyond 10 or 15 at max, right? You don't need it. But even then, like okay, at least it can give us an edge of at least having to deal with 64 kilobyte of memory entirely without wasting anything else. On the modern system, how many you have 32-bit system? Let's see. Raise your hand. I don't see any. All of you are 64-bit. You know, like how much 64-bit can store, can address 64-bit system. 64-bit system is 2 to the power 64. Yes.
4 gigabytes.
64-bit system?
Yeah.
No, 64-bit system. When you're talking about 32-bit system, 4 gigabyte.
Is it like 9 quadrillion values?
Yeah, exactly. Like even 40-bit gives you 1 terabyte memory. You don't have 1 terabyte on your laptop. No way. Do you? Anyone has? No, right? You have what? Like maybe what? Like my laptop has how many gig? 8 gig? 8 gig memory, most probably. Okay, like that. But anyway, potentially with 40-bit, you can address up to 1 terabyte. 64-bit, it is practically infinity at this point, at this age. Okay, maybe 10 years down the line, 64-bit also not enough, maybe, we don't know. But right now it is huge amount of memory, which is not even a part of your main memory system. You need that much. So in that address space, we just moved that IONM, become 1 bit is represented by the IONM, and we just unified the whole access of the memory and the input output devices, because we have so much space we can now use. Okay, and this is modern systems, and this is what is called memory mapped IO. Means we assigned couple of addresses in our memory space to be linked with your IO devices, like 10, 15, 20 IO devices. Rest of them are pure memory device. Okay. Whereas the older system, since we had only limited amount of memory space to be accessed, we had to create one extra complex signal to deal with, and that is called a IO mapped IO system. IO mapped IO system. Memory mapped IO, IO mapped IO. So IO mapped IO is for older systems with like 16-bit system and that so and so forth. Even 32-bit system doesn't have IO in it. 32-bit system input output becomes a memory mapped IO. Like 10 or 15 addresses are specifically dedicated to connect with the IO devices. Everything else is memory. So with that in view, from processor perspective, for a modern computing system, everything is a memory. Processor doesn't distinguish between whether it is talking to an IO device or talking to a memory device. To it, it is just a pure address. Imagine like you are watching a movie on your laptop, like in the screen. What processor or your GPU in this sense, graphics processing unit, all it's doing is rendering the video, send that information, assuming it is sending to a memory, but it is going to a part of the memory which is linked to your display. So that is called your like intermediate buffer and everything. Probably you've heard of that video display, memory, video buffer, that thing. Those are the intermediate memory, but that's complexity aside. Conceptually, your processor is sending that video rendering data, thinking it is writing into a memory, but it is going to a space of the memory, which is linked to your video, and that information being displayed on your display device. So from all practical purpose of understanding your software program mechanism into the system, all you need to understand this simple model. A processor, a memory, they exchange information between them using an address. That's it. So we kind of, yes.
So if we look at this diagram now, the IONM is embedded into the address part now, right?
Mhm. Yes, that's true. So all we did, we started with this complex view and model of the system. Step by step, we kind of tried to simplify it with respect to modern computing system. And from there, what we do a little bit expansion on that to better understand our software program, how it is being executed. We separate, especially divide the processor into three major components: ALU, arithmetic logic unit; controller, which kind of a ringmaster for synchronizing your program; and register file, which is a very fast version, special memory kind of a memory residing inside the processor. And last but not least, one thing is to do the clock system. We'll study more in the next lecture, next topic, what the clock system is. So as I told you, in a very nutshell, your program is being executed step by step, like step 1, instruction fetch; step 2, instruction decode; then execute, then access the memory, then write back the result, like these steps. Now, how do we synchronize the operation between different components in the system, right? So this is right now the best mechanism the technology provides is to synchronize with respect to time. Okay, so it's kind of telling that, hey, this controller asked the memory, hey, write something into this data. And it assumes that it will be done within 3 clock ticks. Like, let's say, tick, tick, tick. Okay. And after that, it can send another. And after that, it can send another. It cannot send before that. Or with the ALU, it sends it and it kind of know, let's say it will generate the result after 5 tick. Okay. So that tick or timestamp is provided by the clock system. So it generates an electronic signal or electronic pulse, as you said, electronic tick, you can also think of that way, in a very uniformly spaced in the time, like very regular signal, it comes up tick, 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 tick. Very fast, okay, very fast, not like a 1 second per second. It is very fast. We'll talk about that. But it kind of gives the synchronization strategy to the whole computing system. So this is a very important part of it. Okay.
I had a
Question.
question.
Yes.
So the controller isn't the one that synchronizes the operations between the memories, ALU, and register file. It's the clock system.
Clock system provide the reference for synchronization.
So it's like the timer.
Yes.
Okay. Thank you.
Okay.
Wait, Professor, I had a question.
Yes.
Wait, so does that mean that the whole program is running at the same speed as the clock system ticks?
Yes.
Okay.
Professor?
Yes.
So the clock system, is it like within the model, like within the processor, or is it outside of the system?
It's outside. This is a little bit complicated electronic system, which generates this signal and fed into the processor and to the memory as well. Okay. Saying that, let's look into what's coming up next day. Okay, for next day, we have this one, lecture, computer organization. So we would talk about this guy has like 6 video part of it. We'll talk about the arithmetic logic unit, its functionality, clock systems, the concept of it, a little bit detail on the clock system, memory system model. From there, we'll derive the register file model, and then we'll talk about the controller. Okay. So the base concept we already discussed today in the first section when we talked about the simple program, how this whole thing get executed. This is more like a detailed on those components. Lecture note, let's quickly go through that. So we'll talk about interface diagrams for the ALU and try to establish kind of a relation with we already understand the concept of libraries and APIs, software APIs. We'll just try to describe our hardware in terms of that. And we talk about the functionality of the arithmetic logic unit. And from there, we'll try to see why we need the clock system more at all in our whole thing. Like, what is this purpose, and how the operations are get synchronized. So we'll talk about that. Then we talk about the memory system model, and again we'll start with the interface diagram or schematic diagram. When I talk about interface diagram or schematic diagram, I talk about the same thing. They're interchangeable term. So we talk about the functionality of the memory, and then we'll discuss about the memory operation with respect to the clock in consideration. Okay, so each clock tick, what action happens, and so on and so forth. This is very important concept for you guys to understand, that how the memory system exactly works in a temporal scale, like in the time scale, what event happens. And then we take this model and derive the register file model out of it. Okay, and we'll talk about that one. And once that is done, then we'll talk about the control system model. And most of it, basically, I was talking about that 5 steps. These are the 5 steps: instruction fetch, decode, execution, memory access, and write back. And we talk about how the program works, etc., etc. So while you are studying these, just keep today's first part in mind, that demo. Someone was asking if I am going to load that slide onto somewhere. No, a slide doesn't make sense. It is all about animation. So I'd say if you want to review, go to recorded session of this in the Zoom, okay, to review that thing. The slide, individual slide that won't make sense to you. Question?
Sorry, I kind of forgot. How do you run your tests again? Is it sort of like, would we expect to sort of generate this sort of stuff, or would it be more like a multiple choice, or you know, how do you run your tests with respect to sort of conceptual stuff like this?
Oh, test means the exams and quizzes?
Yeah, that's right. That's right. Yeah.
Yeah, those are more like an MCQs, problem solving, that kind of thing. We'll explain more like as the time comes. Not worry.
Okay. Thanks.
Okay. All right, any other question? We're just about the time, 8:45.
I've been having some difficulty accessing the Google Drive implementation in the module. I posted a question about it in the logistical discussion.
Okay, yeah.
I think someone else was talking about it too. So yeah.
Yeah, I was having the same issue.
So
I'm assuming that implementation is just to give us the lecture slides. Could you just make that available through like Canvas files or something?
Sure. Have you tried to authorize through your SJC account?
Yeah, I have.
So that didn't work.
No.
Okay. Okay. Do you use Chrome?
No, I've tried it in both Firefox and Microsoft Edge.
Okay. Try in a Chrome and also maybe use your San Jose State profile on the Chrome.
Sure.
And try it out first. Okay. If that doesn't work, I'll do something. I think I have them in the Google Drive. I can send the link. Definitely. Or did module works, or module is also is something like what I'm talking about? Let me share the screen. Right. If you go to the module, right, and it will go to the page anyway. It will go to the page. And you're not actually having this also pop out, because pop out goes to the drive, that link. Okay, maybe I can go to the
Yeah, that's the only part of the page that isn't working.
Yeah, let me see. Oh, I had to I didn't complete the prerequisite as a student. No. Okay. So can one of you come to my next office hour and just show me your problem? Let me try to see what is going on.
Sure.
Okay. And if not, then I'll yeah. In the meantime, like if your friends can access it, they can go to here. And let me see, it is shared by the link, right? Let me see. Why it is restricted only to open with the link? Let me see if I can change it to this. Can you try to access lecture 1 and see now if you can access it? Let me do the same for the lecture 2 then.
No, that didn't work for me for lecture 1.
Not yet?
No, it's still showing the same thing. Yeah, maybe we can jump into office hours and try to solve it.
Yeah, please, come to my office hours and let's try to figure out what is going on.
Okay, thanks.
Thank you.
All right, in the meantime, let me try to share that link in the discussion page so that you guys can at least access them. There is one. Okay, and third lecture too. I'll just put the third lecture in. Okay, I'll remember to put the third lecture. Okay, all right, guys. I think we're well overdue of the time. Thank you very much and good night, everybody, and see you on Thursday.
Thanks, Professor.
Thank you,
Thank
Professor.
you, Professor. Good night.
Good night.
Thank you.